Okay, share the screen. All right, so we are now recording. So today we are basically looking, if you remember at the beginning, we talked about the pillars of information assurance, right? Mm-hmm. And so we've done confidentiality, we've done integrity, right? And the next one that we're going to look at a little bit more is authentication, okay? So we're still obviously using the other ones, but, you know, as you remember, we talked about these as building blocks or the primitives, and using those primitives, we are going to build more complex things, right? So you've seen how we use now symmetric and asymmetric together. So this is a step further, and we are now going to try to address authentication in a very effective way. So that's kind of the general idea of what we're doing today. So we're going to talk about several important things, like I'll start with the digital signature, and then I'll talk about something else called certificate authorities, right? So you probably heard of that, like VeriSign, et cetera. And what do they provide? They provide authentication. Okay, so I'll kind of motivate that. So I have some slides. So I'll start with the slides. Then I have some notes. I'll go with the notes, and then we'll go with the VM and just practice OpenSSL, right? So we've done RSA on Python, but we can also do RSA, of course, on OpenSSL. So we'll explore certain ideas. Okay, any questions? All right, great. Also, I'll try to do at the end kind of a review again of, you know, symmetric and asymmetric encryption, what we're doing with the homework assignment. Don't forget, I think that's due this Thursday and definitely by Sunday. Okay. So this is, you know, this is recording. All right, so I have some slides here. So basically, I'm looking at this folder here, certificate authorities and digital signatures. So I'm going to go ahead and download these, this slide. Okay. It's open. So this is, you know, it should be fun. I think these are very interesting things. Basically here, oops. There we go. All right. So here we're going to look at, you know, basically the certificate, right? So that's one of the ideas that we're going to think about. What is a certificate or a digital signature? Both of them kind of have a similar idea. Okay. So if we look here, a certificate, as I said, is something that is important, that exists. The whole internet requires this to happen. All right. So let's talk a little bit just of the technicalities of it. So we know that we have a public and a private key, right? We have a public key, private key, and I've mentioned to you guys that you generate both of them together. You keep your private key information, right? And then you share your public key. However, to provide more security, let's just say that for now, notice that here in the slides, we have these three boxes here, right? So these three, you can't see my mouse, all right? But those three boxes at the top, these, let me see if I can. Oh yeah, better. All right, so we have this, right? So the public key is this. So we got Bob's ID information, Bob's public key, and then also the certificate information. So basically you're creating a plain text document that's going to contain a public key, Bob's public key, plus some information, including information about something called a certificate authority, which is another entity, right? And it's the entity that's going to help us to provide authentication, basically. So what happens here is this is basically, think of this as just plain text, right? Plain text message. And if you notice, it goes in this direction through a hash function. Okay, something that you already know how to do, like MD5, SHA-1, SHA-256. So the certificate will go through the hash function, and it'll generate what? A hash. And if you remember, that provides integrity, right? So that means that if somebody came to this document and modify it, even just by 1 bit, what would happen to the hash? It would totally change, right? You should know that concept. All right, so then we have this. And then what happens now is you take this hash value and you're going to encrypt it. And how are you going to encrypt it? You're going to encrypt the hash with the certificate authority's private key. So if you remember, when you encrypt something with a private key, it can be decrypted with the public key. Do you guys see that? And so what's important about this is only the certificate authority could have generated that, that encryption. Do you see that? And so basically you're encrypting, you're calculating the hash of the document, creating the hash, and then encrypting it with the certificate authority's private key. And that creates this here, which is basically what is called a signed certificate. Okay, that's the basic concept. Then, of course, what happens is this is attached to it, right? So now you have another party that looks at this document, right? They can take this plain text, you know, maybe Amazon says, this is my public key, right? So what they need to do is they take that document, hash it, and it'll create a hash value. You can see that there. That's the hash value. And then what they can do is they can take the signed certificate and decrypt it with what? With the certificate authority's public key, right? And when you do that, you get this over here. And then what should happen between these two? They should be the same, right? Exactly. And if they are the same, then you basically verified that that public key can be trusted. Does that make sense? So that provides authentication. Now, a key component here is what? The certificate authority, right? So you really have to trust the certificate authority. Okay. And that's something that is usually a company. Google, VeriSign, GoDaddy, Amazon, all of those basically become certificate authorities. But in fact, you guys can become certificate authorities with Linux, right? So we'll do a lab in a few weeks where you do literally that. You'll become a certificate authority and you'll sign some certificates, but that's the basic idea. Now, the weakness of this whole thing, of course, is if the certificate authority became what? Compromised, right? If somehow they were hacked or something, the keys, so then, people, but that's very difficult because this is highly regulated and there aren't that many. I mean, even though anyone can become a certificate authority, there's only a few trusted certificate authorities, okay? So we'll see later on how you can do that, how you can add the certificate authority into the browser, since browsers are the ones, your web browser, that have certificate authority. So if you want to think of, okay, where is this public key that you speak of that belongs to the certificate authority? That public key is in your web browser. So if we'll see in a few weeks when we do the lab, I'll show you how to go into the browser and look for these keys. Okay, make sense? All right. So anyway, this is an important concept, and as I said, what I'm introducing here is authentication. Now we could have just taken that document, right, the plain text document, and encrypted that. But what's the problem with that? The problem with that would be that when you decrypt it, you would literally have to read it, right? Semantically read it to see if it makes sense. Whereas if you use a hash value, then it's fully automated, right? So you can automate, you can do the checks totally automatically because you're going to get this document. You know what the hashing functions are. So you generate the hash. Then you're going to have attached to it the hash, the original hash that was encrypted with the private key of the certificate authority. In your browser or somewhere, you will have the corresponding public key. And so that you can decrypt that as well, and they will both match. Any questions? And that is how you achieve authentication with RSA. One of the ways. Okay, right. So yeah, so this is, one of the concepts. There's other things you can do. I mean, you can play with these ideas now that you understand how to use all these primitives. You can combine them in multiple ways to achieve, interesting objectives, right? Something called a digital envelope. So it's just kind of interesting. Protects a message without needing to first arrange for sender and receiver to have the same secret key, right? So basically, the idea is you're just going to send this out, right? So you have the message, and you're going to encrypt the message using symmetric encryption, right? So that's the encrypted message. So this is the symmetric key that you decided to use, all right? And then you're going to also attach the key to the message, but of course you have to encrypt it. So then you do the encryption, and you're going to select what? The recipient's public key. Very good, right? And then perfect. And then you send both of them encrypted. So then, just notify the recipient, hey, I use your public key. Okay, so then the recipient will know, okay, perfect. I'll take the key. They're going to decrypt it with their private key, which only they have. And then once that happens, they have the symmetric key. And now they can use the decryption algorithm, such as AES, to take the encrypted message and obtain the plain text message. Make sense? I could ask you, for instance, on a quiz or an exam or a homework assignment, just to do this one, just to, you have all the tools now to be able to accomplish these. And yeah, so this week, I'll show you OpenSSL a little bit more and how you can, do more things with OpenSSL. The one advantage of OpenSSL, I should say, is that it does generate all the files for you. So it does become a little bit easier in that sense. Okay. All right, so digital signatures, just a little bit of information. So suppose Alice sends a contract agreement to Bob, right? So to avoid legal troubles, we'd like this communication of contracts to have the property of non-repudiation, which is a type of authentication, right? Bob should be assured that Alice can't back out of the deal by claiming she never sent the contract, okay? Likewise, we want the property of integrity. Alice should be assured that Bob can't modify the contract and claim that the modified version is what Alice sent. Okay, so that's the other idea. So Alice should be still recording, right? Okay. All right, so I think it's still recording. So let's continue. Okay, so likewise, we want the property of integrity. Alice should be assured that Bob can't modify the contract and claim that the modified version is what Alice sent him. There's a nice technique called the digital signature that provides these guarantees, okay? So this is the concept that we're trying to understand. Alice simply computes a hash of the contract agreement, encrypts that hash with her private key, and sends the result, which is the electronic signature, along with the contract to Bob. So you have to send that. Anyone can take the contract, hash it, and compare the result with what you get when you decrypt the electronic signature with Alice's public key. If it matches, then the contract must be exactly the same as what Alice sent, okay? So Alice must have sent it because only Alice can encrypt something that decrypts properly with Alice's public key. And the contract can't have been modified because the hash value would have changed, right? So you understand those ideas. Any questions? All right, so that just kind of summarizes the whole thing. Okay, so finally, so that was digital signatures. Now let's talk a little bit about certificate authorities and motivate that a little bit. They're kind of the same idea, okay? So asymmetric, and sometimes this is called a man-in-the-middle attack in the sense that, somebody could pretend to be you, right? And say, oh, this is my public key. So asymmetric public key encryption is almost magical. You create security out of insecurity, right? However, there is still one weakness in the system that's fundamental. You see on a website something like, hi, I'm Bob, and my public key is that, right? So you guys recognize that this is the encryption exponent, and then this is the modulus, or n, right? But how do you know that public key really belongs to Bob? You know what I mean? Like I have a website and I put my name, it's my website, right? And I put my name there and I put my public key. But how do you really know it's my public key? Somebody could have hacked my website and put another key there, right? That's a possibility. So while you can, so that's the thing, it's not the website itself, but the file that you're putting there, right? The key that you make available. So you want to do something extra around that key that you're putting there to provide additional security. It's like that key gets wrapped around something else that you can trust. And that's basically using someone else's key to encrypt, okay? So while you can be assured that if you encrypt a message with this key, only the key's owner will be able to decrypt it, how can you be sure that that key's owner is really Bob, right? That's the kind of like the foundation or the justification of all of it. If you trust the website on which the public key is posted, you might be comfortable, right? And that's what I was saying. You might trust the website. But we know that websites can be hacked, right? That's something that can happen. So, but at the end of the day, you have to trust whoever is presenting this key as belonging to Bob. And that trust is a security weakness. All right. So people then decided to solve that with the certificate authority. All right. So that's kind of the motivation of that idea. Does that make sense? So we'll talk now about certificate authority. So I have some notes. We'll go over that. And then, as I said, we'll play with OpenSSL. Since we're on Brightspace here, let's take a look at this week's assignment, just so that you get a sense. So it's here, digital signatures homework. Okay, so basically, the assignment this week is two things. Performance, so we're going to take a look at performance of a comparison of symmetric versus asymmetric encryption. And we're also going to look at creating digital signatures. All right, as you might imagine, one of the things I'm going to ask you to do is to work with your partner and do what? Achieve authentication, right? So it's kind of the same problem I always give you. And then I'll demo some of these so that you know how to use it. So this, I'll write some code on Thursday, how to do the performance check, but it invokes OpenSSL so that we have something very solid. And then this is just OpenSSL. So let's take a look at the problem. Create a digital, number two, I'm reading number two. Create digital signature. In this task, we will use OpenSSL to generate digital signatures. Please prepare a file, such as example.txt, of any size. Please also prepare an RSA public and private key pair. So this time around, we're going to learn how to create these with OpenSSL and then do the following. Sign the SHA-256 hash of example.txt. Save the output into a file named example.SHA-256. Then you're going to verify the digital signature in example.SHA-256. And that's basically, I'm going to demo this to illustrate how digital signatures work. Then after that, what you will do is you will modify one bit of the file and then repeat the process again, just to show that if we change even one bit of it, the digital signature will not check out anymore. So it's a similar idea to what we've done before. Okay. And then this top problem here is basically performance, a comparison between RSA and AES. So we're going to run OpenSSL about 10,000. We're going to do an encryption about 10,000 times with RSA and then encrypting the same file. And then we're going to repeat it with AES. And basically, you're going to measure how long it takes. And the idea is to try to create a scenario where you can compare the performance and kind of, you should see that RSA is slower than AES. Does that make sense? So those are the two problems that we're going to tackle on Thursday. Okay, and then of course, I'll add the third one. I haven't done so already, which is basically work with your partner and achieve authentication. So probably exchange your key or something like that, okay? All right, so that was Brightspace. Now we can talk a little bit about certificate authorities, which is the other important concept. So remember, if you're ever, write down in your cheat sheet, if you think of certificate authorities, just think of like VeriSign, right? The company. And then that'll give you a sense of what it is accepting, okay? But you should also understand how they're achieving it, which is basically just using RSA. I mean, they're not using anything, any magical thing. All right, so we are going to need actually, let's wait on certificate authorities and let's just switch to the virtual machine and do the other. Right, so you can start your virtual machine and kind of follow along. This is important because some of these commands could be on the practical exam, okay? They may not be on the homework this week, but they could be on the practical exam. So one of the things that we did in last week's quiz, right, is what? You factorize n. Do you remember that? So I created a scenario, I gave you n and you had to find the prime numbers. So I'm going to try to do that now with OpenSSL. I'm going to try to repeat that, but I want to show you what happens, okay? All right, so the VM is starting. So OpenSSL generates these .pem files by default, right? And these PEM files are going to contain our public and our private key, okay? And so that's really, if you want to break RSA, you need to be able to extract information from these PEM files, okay? So that's kind of what I'm going to do. So the first thing will be that we need to generate some PEM files. Okay, so let's open up terminal. Okay, so I created this before the class, certificates. And then I'm going to create a new folder. So it's empty. So you may be interested in extracting the number of parameters N and E from a public key, right? And the reason why you might want to do that is you might want to break RSA by calculating the prime numbers associated with N. So you want to do this in order to check if the modulus N is factorizable or has previously been factored by someone else. So that's another thing that might have happened, that there may be some numbers that exist in a database that might take a long time to break, but they may have been used before, and so you can just search to see if they're available. Now, many folks still use 1024 RSA, despite the fact that that modulus of that size has been factorized successfully, okay? So just keep that in mind. Now, if you remember when we did the quiz last week, I used a seed size of 16. Now I'm talking about a seed size of 1024 bits, which is pretty large, all right? I tried doing this before with FactorDB and I was not able to factorize that. But that doesn't mean it's not possible. Okay. All right. So let's go ahead and try to do that. Now, another thing that we're going to try to generate is actually a certificate, and that uses a format called X509. Okay, so just be aware of that. All right, so let's use RSA in OpenSSL. So OpenSSL request -new key RSA 1024. So this is where you specify the seed size, okay? Then you're going to say something like -days, and that just means, so whenever you create a certificate, you also specify how long you want that to be valid. And after a certain period of time, it's not going to be valid anymore. So here you can say 365 days -nodes -X509, which is that format for the certificate. So it just makes sure that all the certificate templates are consistent. -key out, and it's going to be test.pem. So these are the famous PEM files that we will be using quite a bit. These are generated both by OpenSSL and also by something called PyCryptoDome, which we will use later on. And then also the certificate -out test.cert. Okay. All right. So if I hit now, before I hit 1024, I'm going to start with smaller values. So in the Python code, I could do way smaller, right? So I could do 16, for instance. So try that. And you can see it says key size is too small. So it's not actually letting me do it. And that probably makes sense because it's insecure. Easily, we've already broken something of this size. We know that we can break it with FactorDB. So it's not, I don't know if there's some setting in OpenSSL that we could change and and control that, but by default, it's not letting me do it. Let's try another one. Let's jump to like 64. See, it's still too small, so it's not letting me do it. Okay, let's try 256. Also too small, so it's doesn't like it. Let's try 512. Okay, so 512 was allowed, right? This is interesting because let's go with 512 to see if, we can break 512 with FactorDB. Remember, the challenge is that we're going to need to rely on a supercomputer, which in this case would be our website FactorDB. Does that make sense? All right. As I said before, I tried this with 1024. I was not able to factor in, but maybe with 512. All right, so let's read the information here. So it says generating an RSA private key, okay? Writing new private key into test.pem. So that's the name that I've given it. Probably I should have written private.pem instead. So you're about to ask to enter information that will be incorporated into your certificate request. So remember that not only are you creating a key, but then you're going to generate a public key, and you're going to sign that public key with your private key. And that is called a self-signed certificate. Does that make sense, guys? Okay. All right. So you're about to be asked to enter information that will be incorporated into your certificate request. What you're about to enter is what is called a distinguished name, or DN. There are quite a few fields, but you can leave some of them blank. But it's really important that the information, like the common name, especially if you're doing this for a website, match exactly what your website is, because a browser would take the public key, look at that name, and make sure it matches the URL. Otherwise, it would not allow it to run. Okay, you'll do a lab about that. All right, so here you enter the information. So enter Indiana. You can enter Hammond. ENW. You can leave that blank. Common name, I would just put PNW here. Email, you can leave that blank. And that's it, right? So if you notice, we entered some information, and now we have generated two files. Notice the test PEM is a private key. It's a file. If you look at this information here, what do you think that means?
Only admins can read-write it.
Only admins can read-write it. Not quite. Nobody? All right. None of you have taken 372? All right. When you take 372, you will know what this means. That's the Linux class. But basically, it means that only the owner. So in this case, the owner is seed, and only seed can read and write, which is great because this is a private key. You see that? So only you can read your own private key. Got it? So by default, OpenSSL does that. This means that the owner plus also the group and everyone else in the system can read it. Okay, so the R means read, the W means write. All right, so now let's take a look at these files, okay? So I'm gonna do cat test.pem. What do you see there? So that's the private key that I generated, and I used 512. So hopefully we'll be able to factor this with FactorDB. That's really my objective. So I'm kind of repeating the exercise from last week, but just with bigger things. All right, so that's the private key. If you have a private key, you can use OpenSSL to generate a public key. Now let's take a look at test.cert. Also, when you guys do this, make sure to put your names on it. So you can say like Bob public, Bob private, you know, and Alice public, Alice private, just so that you're basically, you know, don't get confused. Okay, so this is the, what is this? The certificate. Okay, so this is the certificate that we have here, but we can't really make out a lot of the information, correct? You guys see that? So we're gonna now kind of start to drill down into these things with OpenSSL with the objective of extracting the parameters that we might want to use, okay? Got it? All right, so let's go ahead and do that. So one contains the new private key for the 512-bit RSA, and the other one contains the X509 certificate that contains the public key, and a self-signed version of the same. So all that is formatted in there. So now we're gonna look at a command that will print out a mess. Let's see. I think this one will generate the same key, but more readable. Yeah, so this is how we're gonna generate more readable information. So we're gonna do OpenSSL X509, oops, X509 dash in test.cert, right? So test.cert is this one. We couldn't really make it out, right? What it's in it. So we're going to try to make that a little bit clearer. So dash text dash no out. Okay, so now let's try it. And as you can see, now we have more readable information about the certificate, right? Which again is a self-signed certificate. So it's kind of fun that way, because it's signed by your private key. So what do we have in here? We can take a look. It says the certificate. There's a serial number. We'll talk about these parameters. So that's the thing that I was the notes that I have, but I'm gonna leave that for last. So the serial number, I think it's a serial number that's assigned to you as an entity. The signature algorithm is SHA-256, so that tells you. So I no longer have to, if I give you something like this, I no longer have to tell you which hash I use. It's right there, right? So you have to dig these things out. Okay, it's got your parameters in here. The validity of it, see, it expires in 2024. It's got P&W, the common name, which is pretty important, right there. This one. So it's got the public key algorithm, RSA encryption, which you know. This is important, right? 512-bit. Okay, this is the thing. If you saw something like that, you'd be like, maybe I can factorize with this computer that I have. So you got to pay attention to that. What is this? Modulus. What is the modulus?
Remainder.
Yeah, yeah. I mean, mathematically speaking, I guess, but sometimes n is called a modulus. Okay, so keep that in mind. So it's n. So that's the thing that you want, right? And then what is this one? Notice that it's a common number that we have seen before. It's the exponent, so it's which letter? E. Very good. So that's your public key, E and N. So if you want to factorize this, you got to grab that one and take it to FactorDB. Got it? All right. Then we've got some additional, the subject identifier, the authority identifier. So these are things that you don't need. And then here is the actual signature, because it's a self-signed certificate. Obviously, what you would want is for this to be signed by another entity, such as VeriSign. So if this ID said VeriSign, right, and you have a signature that says VeriSign, what does that mean? It means that VeriSign used what? Their private key to generate this digital signature, which means that you would use VeriSign's public key to verify. Does that make sense, guys? And that's how you would do it. So that'll be one of the problems on Thursday. Any questions on this? Everyone understand that this is the n that we would want to factorize to be able to break this, okay? All right. So this displays in the terminal window any information that we've supplied, such as ham and P&W. And we have the public key in there by having N and E. So that's available. So it's kind of what I gave you in the math, but now you can see it actually as you would see it formally. There's the signature. Now this is called base 64. So we do have that problem, right? That FactorDB requires this to be an integer. So we're going to have to solve that problem, but that's not a difficult one. I've already posted the code on the Brightspace on Github. Now let's say that you want to see specific parameters. You could also grab those. So we're going to do some examples of that. So let's generate some new keys now. Let's try something. So let's go ahead and call OpenSSL gen RSA dash out. And now let's say Bob private key dot pen. And again, I'm going to try 512. Okay. So that then it says generating RSA private key, 512-bit long modulus, 2 primes. And E is 65,537. So let's do ls-l. Cat Bob private. And it says it's the private key. Now we're going to generate the public key from this private key. So you can see I've generated a private key, and now I can generate the public key from it. So I'm going to do open SSL RSA dash in Bob private key dot pem dash pub out. Okay. Okay, and I'm gonna generate Bob public key dot pem. Got it? All right. So what did I do here? Again, if you don't understand this, these are concepts from 372, the Linux class. But basically what I'm doing is I'm using OpenSSL, RSA. I grab the private key, and this is called redirection. So I'm just redirecting to another file, which I'm calling public key, and I'm going to store the public key there. So these are, so if I ever say, you know, please guys, we're going to do an RSA exercise, generate your public and private keys. These are the commands. So write them down in your cheat sheet. Okay. You can now, all of you, generate very professional public and private keys. Okay. So very important. Got it? And really very secure ones, because this, you know, I'm using 512 because I want to break this, but you can do 4096 and so on. All right, so hopefully that worked. Let's do clear action. ls-l. So I've got, notice again, the permissions are really important for Bob. I do strongly, you know, when you guys work with your partners, name your keys like this. Bob, you know, Bob, Alice, John Smith, you know, whatever it is. That way you will know. One thing that you should never get confused about. Whenever you're encrypting and decrypting, it has to be these that correspond to each other, right? So if it's Bob, you use Bob's public and private keys. All right, so if you notice, once again, the private key, only the owner can read and write it. And the public key is available pretty much by everyone to read. Sorry. All right. So I've got my keys here. Now what we want to do is we want to extract parameters from them, right? So I may give you just something like this on the exam or the practical. I could give you Bob public, right? And so, and I ask you to break it, but you're like, okay, you know, it just looks like that. So you need to extract parameters from it. Okay. So if you want to extract the number of parameters from a PEM file containing a private key, you can try the following. So let's try OpenSSL RSA batteries. All right, so sorry. So we want to generate some parameters. So let's do OpenSSL RSA dash text. And then we're going to redirect into this command Bob private key dot pem. Just like that. And there you go. So if you remember, I said to you guys that in the private key, for convenience, you actually store the prime numbers. Do you remember that? So we talked about it. So as you can see, they're there. This is the private key, and it's telling you some important information, right? So it says RSA private key, 512-bit. This is important because it gives you some notion as to the type of supercomputer that you need to break this. It says 2 primes. Again, what is this? N, very good. And the public exponent is there. It's got everything, right? And then it's got the private exponent. Notice once again that the private exponent is much larger than the public exponent. And then for convenience, it's got the 2 prime numbers. This one and that one. Do you see that? And it's got other parameters that it has available in there and the notation like this. Okay. If we want to do the same thing for the public key, so to do the same for the public key, let's try that. So I'm going to clear this one. Open SSL RSA dash text dash pub in, and we're going to redirect into this command Bob public key. Okay, and there we go. So we're going to try to repeat the same idea. So I hit enter. Notice this one has a little less information because it's not the private key, but it does have the N, the modulus. It's got the E, basically. Got it? All right. So now you guys have ways of extracting this information. If you want the modulus to just be printed out, you can try open SSL RSA dash text dash pub in dash modulus. And we're going to redirect into this command the public key. So that's going to be Bob public key.pem. And there it is. If you notice, now it's printing this one over here. That's your modulus, but it's your modulus in what? In hexadecimal. And factor DB requires what? An integer, right? So we still need to solve that problem. Okay, just another one, I guess, for the certificate. Since we did the keys, but let's do one of the, let's see. We had generated test.cert, so let's look at the certificate. Open SSL X509, which means certificate format dash text, and then we redirect into it test.cert. And there you go. So you've got all the information of the certificate itself. All right, so now let's try to do something fun, right? Let's try to factorize Bob's public key, the modulus. If we can do that, we can break the whole thing, right? But it's difficult. So like I said, I don't know, because it's 512 is pretty big, if factor DB will be able to do it. So how do I do this? I posted some code on GitHub to be able to convert a hexadecimal modulus or n into an integer. Let's do that. All right, so this is to convert a hex to decimal. All right, so we're going to do, I'm gonna create a variable first. So let's start like this. So let's do cat of Bob, right? Bob public. So you guys understand that for this public and private key, right? Which is 512-bit, if we can extract the end from there and we're able to factorize it, we have a way of breaking everything, right? So that's the key thing. But the challenge is the size is so big. So let's try with 512. So I'm going to create a variable here. Hex modulus. Okay, and I'm going to extract the end from the public key. Okay, so that's from the public key file. So then you can do basically that, you know, if I had the public key, I would just write it there. Okay, that's what I'm saying, right? Like that. But instead, we're going to extract it from the file. So I'm going to do OpenSSL RSA dash pub in dash in Bob public key dot pen. Okay. Then we're going to say dash modulus, that's the end. So we're extracting the modulus as we saw in a previous example. And we're going to pipe this. So pipe is another command in Linux that allows you to redirect. So we're going to pipe this information into another command called grep. This is also a command from 372. You guys will learn about grep and how to, so it's basically like an Excel type of thing. Like if you grab 3 lines out of 10, if you have a match, it's like an if statement that matches. So you're saying grep from that modulus equal. Okay. So this is something that we had in a previous command. We saw the modulus written like this, right? So grep this modulus. And then from that, we just want to get rid of a part. All right. So what you're going to do is just type cut dash D single quote equal and then dash F2. Okay. So that should give you the end. Okay. From the certificate, just run this command, type it up, and it should work. Right. So if I run enter, okay, it should have done it. And it should be in hex modulus. And there it is. Okay, so it's like a variable that we created on the terminal. And it's, you know, using the terminal, as you guys will learn in 372, is sometimes very useful. It's very fast, very powerful. And you can save a lot of work. All right, but as you can see, it is hex, right? So it is hex. And that's the problem that we have. So now what we're going to try to do is to convert it into integer. You can double check. So we can do cat. What was one of the commands? So OpenSSL RSA text pub in modulus Bob public key, right? So you can see it says 5C here, and it says 5C here. You can see it says E1 here, and it says E1 there. Okay. And then it starts at 00 AB E5. So AB E5. Okay. Got it? So we've grabbed it as in this, you know, one important thing is if you look, they're in different formats. Okay. This one kind of looks like this, and this one kind of looks like this, even though they are the same information. Got it? All right, now we want to convert it into integer. And once we have it as an integer, we can try factor db. So you will need to install Ruby for this to work. Ruby is a programming language like Python. I mean, I could have done this in Python, but I found some Ruby code. All right, so yeah, I'll be honest with you. So just type this exactly, or do the research and find the Python equivalent or the Bash equivalent. I mean, you can do it in multiple ways. But to be honest, that's why I did it. All right, so sudo apt is a command to install on Linux, right? So just do sudo apt update. Okay, that just updates the repository. So if you're familiar with Linux, for installing things on Linux, so definitely do that first. If you don't do it, it might give you an error when you try to install Ruby. All right, so just please go ahead and hit enter, update your repositories. Okay, so hopefully that's done. Now do sudo apt install Ruby. I already did it, so mine's going to be there. But for you guys, it's going to ask you, I think, yes or no. So just hit Y for yes, and then see the installation to the end. Got it? So let me know once one of you finishes, please. Got it? All right, thank you. All right, so Ruby is installed. So now we're just going to add a few commands on the terminal, and basically this should convert. So let's do clear here. We've got Ruby now, so just type Ruby. Like this. And as I said, all of this is on the GitHub under the RSA folder. So Ruby less than EOF. And then type P, lowercase p, double quote, $, hex, that's the variable, modulus, double quote, and then we're going to convert it. So just say to lowercase 2 underscore I16 dot 2 S. Okay, and then EOF, and there you go. So as you can see, this is what I did is not really like so important for the class. You can do it in many different ways, but really what I cared about was getting this number, right? So converting the hexadecimal that we had before into this. If we look at this carefully, it is all numbers, correct? It's all numbers. So this would be the n as a number, which is something that we know how to take something like this into factor db to see if we can factorize it with 512. Okay. So this I've shown you with factor db, as I said before, that if it's something is like 16-bit, you can break the n, but breaking something this large may not be possible in that website. It is possible up until 1024, but you have to have, better resources. So let's go ahead now and open up the browser. factordb.com. Okay. And we're going to paste this value in there. So as you can see, it's pretty large, and just hit factorize. And I don't believe it was able to do it as it is pretty large. So you can see it didn't give me the 2 prime numbers. It's just too big. So this kind of shows you at least that there is some security, right, with the larger size of the keys. It just doesn't have it. It doesn't have it in the database, and it wasn't able to factorize it either. Make sense? So you can imagine that if it's 1024, it's not so easy for somebody to break it with resources available online, but that doesn't mean that it cannot be broken with the right resources. So for instance, one thing that you could do this semester for the term project, which actually we need to talk about that this Thursday, because we're getting close to the end of the semester, is this could be a project for you. Not using FactorDB, but other resources. Can you break an RSA modulus that is 1024, for instance? You see what I'm saying? So that would be a nice project. Project doesn't have to be very big. It's only 10% of your grade. And so something like that is a good one to do. Something fun like that. Anyway, that's the idea. So obviously, why is this important? It's important because if on the practical, I give you a public key that says 512 or 1024, you should ignore it, right? Because all you have to break RSA or factorize the primes is FactorDB. So obviously then I may intentionally try to trick you, right, to look at that information, okay? Make sense? But otherwise, if we had something more powerful than FactorDB, this would have been the process. Everything we did and then factorizing it here would have been the process to break RSA. This would have given us the primes, and then with the primes, we could use our code to break it. Any questions? Got it? All right, so let's go back to the terminal. Okay, so we did several things today. We looked at how to generate our public and private keys. We've looked at how to extract parameters from these. Now, another thing I could do is I could just manually modify the public key, right? And if you see 16-bit or 32-bit in there instead of 512, and you see a modulus in there, it may be that one can be factorized. So don't forget those little hints, okay? Because they may be key to breaking the challenge. Yeah, so after you have become comfortable with OpenSSL, you can output modulus and the public exponent. You know how to extract them now. And then you can feed these into a Python script and try to factorize it that way as well. And I've shown you how to create the integer representation, so you know how to get to that. And then you know that you could try it with something like FactorDB. Okay, all right, so that kind of concludes that section of just generating public and private keys with OpenSSL. You now have the tools to create your public and private keys and be able to do any kind of exercise where I ask you to, we'll see digital signatures shortly or later, I mean this week, but you can generate the keys and now do authentication and so on. All right, so let's look at the certificate again. Okay, so this is the certificate. All right, so the parameters in here are so a certificate has, the format is something called x.509. And the different fields in the certificate are the version number, which describes the version of X509 that you're using, serial numbers, This is a serial number assigned to the certificate by the CA. Okay, so you see that in there somewhere. There's a serial number here. So that is a serial number assigned to a certificate by the CA. You see the signature algorithm ID. So that's the SHA-256. Okay. The issuer name, which is the name of the certificate authority that issued the certificate. Okay. So that's the issuer. You can see that here. So in this case, PNW, I guess. The validity period. So that should be in there somewhere. Right here, validity. Right. So that's how long it's going to be available. So this field states the time period during which the certificate is valid. The period is defined with two date times. The subject name is, this field identifies the individual organization to which the certificate was issued. So in this case, PNW. So that's why this is a self-signed certificate, because if you notice, both of these are PNW, right? If it was VeriSign, then this would be PNW and this would be what? VeriSign. Make sense? Pretty straightforward, I think. Then we have the subject public key, which, as you know, is made up of N and E. Okay. So I'll summarize that the definition of a signature, that a signature is obtained by first computing a message, digest, or hash from the rest of the fields with a hashing algorithm. Okay, so you're going to take a look at all these fields, right? Including, very importantly, N and E, which are the public key, right? And you're going to calculate a hash of it. So using something like SHA-256, I think. Yeah, SHA-256 right here. Okay. And then encrypting it with the CA's, the certificate authority's private key. Authenticity of the contents of the certificate can be verified by using the certificate authority's public key, okay, to retrieve the message digest and to compare the digest with one computed for the rest of the field, basically. So we had said that before. Any questions, guys? Making sense? It's nice, right? I don't know. I find it so interesting. Apparently you guys, it's exciting stuff. I mean, this makes the world work. I don't know if you realize, nothing would work without this. This is what we would, you know, the whole internet works with this. All right. So certificate authorities, I've talked about this, so I don't want to be repetitive. All right, so let's just go into the lab, right? So let's start with that. Let's do the digital signature problem, okay? So let's go ahead. And so let's go ahead and start with that. We're going to do a digital signature. So let's create, okay, so now I'm shifting gears, right? And we're going to do problem 2. So this is problem 2 of the homework. Okay, that's problem 2 of the homework. I'm going to demo it. Remember, though, what I want you guys to do in that problem is to actually exchange that with your partner, which means you have to do everything. Create public and private keys, you know, and various things. So I'll think of some, I haven't written that third problem yet. All right, so let's start with creating a file. So let's call it example.txt. Okay, and just put your name on it. Hello. You know, today is Tuesday. Yeah, Purdue. So Purdue University North. Okay, so save that. So we have a file now, ls-l. Okay, so now we want to create a digital signature, okay? So we haven't seen how to do that. And OpenSSL actually has commands for that. So it's not like we have to run all the things independently. It's got a built-in command. All right, so let's try it. So we're going to do first OpenSSL gen RSA. OpenSSL gen RSA dash path out pass. Notice it's like you're generating a password basically. So to add a little bit more security, so 13579, you can do it without this. And then you're going to say dash out. And now I'm going to use a name. I'm going to use Alice. I'm going to say Alice private key dot pen. Okay. And so that's dash out Alice private key dot pem. And then of course we specify the size. 1024, basically, as you have seen in today's lecture, we can't factorize these with FactorDB. But in the literature, it says that this has been broken already, so it's insecure. Okay, so let's go ahead and do that. All right. ls-l, so Alice now, we can cat it. And you guys know I'm not going to repeat how to extract all the parameters. Okay. So our objective is that we want to do a digital signature. So we're also going to generate the public key. So I'm going to do OpenSSL RSA dash pass in pass 13579 dash pub out dash pub out dash in. To be able to generate a public key, here we need a private key. And so we're going to do Alice private key dot pem dash out Alice public key dot pem. Okay, so that should work. We don't have to specify 1024, etc., because that's in the private key itself. Okay, good. Let's dash L. So you got your app. So each of you needs to create these keys. And I suggest you put your name, associate your name with them. So, you know, Ben, private key, Ben, public key, Nathan, public key, Nathan, private key. If you guys are working together, you need to know exactly which keys you need to use, right? So that's one of the challenges of this, the fun of it too. All right, so now that we have the keys generated, we can take a look at it. We haven't done so already, so you can say Alice pub. Okay, as you can see, we verify it's a public key, it's smaller, and you know how to extract the different parameters. I already showed you. All right, so now we have that file example, and that's, you know, let's say it's a contract or something, right? You know, like we did in the example. Maybe it's an exam. Maybe I decide that on the second exam, I'm going to give you two, and I'm going to say only use the one signed by me. That could be a question on the exam, right? All right, so anyway, so you have this file, and now you can go ahead and let's see, we've generated the public and the private key. Now we're going to try to sign example.txt. Okay. And we're going to use SHA-256 as the hashing algorithm. So we can try open SSL. Okay, let me write this like this. Now we sign example.txt. Okay, so that's what we're doing now. We're going to sign example.txt. So you can type OpenSSL DGST digest dash SHA-256 dash sign. We sign with what? We sign with the public? Private key. All right. So remember that, so it's Alice in this case, let's say private, right? Oop, I shouldn't have hit. Sorry, I hit enter. Okay. So we sign with the private key, right? And we're going to do dash out example dot SHA-256, and the input to this is example.txt. So remember, we haven't actually read in example.txt. Okay, so now we should have everything that we need. So if I hit enter, yeah, it should work. So now I should have a file example.SHA-256, and there it is. Do you guys see that? Does that make sense? Okay, great. Of course, as usual, you can do cat example SHA, and as you can see, it's some kind of an encrypted thing. Any questions? So that's a signature. Now we want to verify the signature, right? So where do you verify that? So that means you're going to send this over the internet, right, to your friend across the world, and they're going to verify. So let's try it. Let's do clear here. ls-l. So we're going to do OpenSSL DGST dash SHA-256 dash verify. We need a key. What key do we use? Public. Public. Who's key? Alice. See, very important that you think about this. So Alice, public key. We can tab to complete. So Alice is public key, and then we're going to say dash signature. Okay. And the signature should be the file that you received, which is example.SHA-256. Okay, and also, what else do we need? It's in the diagram. So we've got the keys, we've got the signature, but we also need the original file, right? Example.txt. Questions? Does this make sense, guys? Yep. All right, so now let's go ahead and hit enter. Verified okay, that's all it gives you. That's all you need. But it does that for you. It's like an if statement, or a function that just returns true or false. So in this case, assume it returned true, and it means it checks out. So let me ask you, I could give you this scenario and then ask you multiple choice. Which principle of information assurance was achieved with this approach? Confidentiality, true or false? False. Why? You're right, but why?
We had to put in the original.
Yeah, example txt is plain text, right? We didn't encrypt. So now could we do it with and achieve confidentiality? Sure, we could. But what would we have to do? We would have to take example txt, encrypt it, and then send that. You see that? But in this particular case, we did not achieve confidentiality. True or false? Did we achieve integrity?
No.
No? Why did we hash it first with SHA-256? So we are automatically achieving integrity, right? Because that's the first step. We actually hash it with SHA-256, and that means that it wasn't modified. And that's the next thing that we're going to do now. We're going to corrupt the file. So if it gets modified, then integrity has been affected. Got it? True or false? Was authentication achieved?
Yes.
Yes. I mean, that's like today's topic. So as you can see, if you ever thought of authentication, maybe the first thing that comes to mind is what? Passwords, right? We all think of passwords and we think of authentication, but maybe it wasn't clear to you that authentication could also be achieved with cryptography, and it can, and this proves it. Got it? Again, to achieve one weakness of this scenario is who signs, right, with their private key. So we can do self-signed certificates, but really what we want is to have it done by a certificate authority, which is an actual entity such as VeriSign. This is heavily regulated. The FBI and institutions like that are all over it. And if something happened to VeriSign, like if you tampered with them, you're going to go to jail. I mean, it's very serious stuff because it's like the weak link. Okay, so very important. All right, it is verified. Now we're going to change a letter in example.txt, which changes what? If I change a letter, we don't have to change a bit. We can just go in and change example.txt and just change one letter, change it to 4, right? But what does that mean? It means that the file now, if we change one bit, even one bit of a file, what happens with the hashing algorithm? It generates a completely different hash. And then we're signing that. So what would you expect here? The integrity has been compromised. And so it's not, the signature itself will no longer check out. Okay. So I'm going to repeat the exercise because I already modified example by changing one letter or one bit. So now I'm going to do this one and verified failing. Do you see that? Just by changing one bit of it. That's basically problem 2 of the homework. Like I said, I'll come up with some new problems on Thursday, but this gives you a scenario. The problem of performance is a little bit too involved, so we'll do that one on Thursday because it's a bit of coding. We'll be writing in Bash or something like that. Okay, so yeah, so we'll do that Thursday. Let me just check my notes, make sure I didn't miss anything. So how does a certificate authority, sign a public key? Let's say, do any of you have a public key signed by a certificate authority? No, right? None of you. I don't have one. Most of us don't, right? So who needs to have their public keys signed by certificate authorities? Companies, usually. Amazon, right? Banks, Chase, Bank of America, Wells Fargo. So they need to have it. So really the number of institutions or entities that need to have their public keys signed is small, right? Within an institution, if you're like a IT person in a company, if you have an intranet, sure, you can create a whole bunch of certificates within the organization, and you're the master of that domain. But in the overall internet, which is highly insecure, right, you need to have something that's trusted, right? And so there, you have something like a company like VeriSign, and then you don't really have that many people or entities that need to have their, relatively speaking, that need to have their keys signed, right? So think of the case of Amazon. So if Amazon wants to have a public key so that they can engage in communication, which they do, secure communication, what do they do exactly? They may go to the offices of VeriSign with lawyers and everything, sign contracts, pay, and then they check their identity. So they'll go, okay, you are Amazon, the institution, sign, and then the certificates are generated. You see that? And then Amazon will use this. Does that make sense? So they basically, that's where that has to happen, an in-person kind of thing, so that they can definitely check that this is a bank, that this is Amazon or eBay or something like that. And then their public keys get signed by the private key of the certificate authority. So that can happen in real time. I'm sure now there's some automation to it, but in general, my point is, you really want the certificate authority to check out who that person is or company to make sure they are who they say they are. Got it? Does that make sense? So that's one thing that's a little bit like not fully automated. And it requires checking identities and things like that. All right, great. So that's the certificate authority. So to obtain a certificate, a user presents his public key to the CA. Said simply, a certificate is your public key signed by the CA's private key. So CA-based authentication of a user, like a company like Amazon, is based on the assumption that when a new user applies to the certificate to the CA for a certificate, the CA can authenticate the identity of the applicant through other means, okay? So outside of cryptography, which is, like I said, presenting IDs, contracts, constitution documents, etc. At its minimum, a certificate assigned to a user consists of the user's public key, the identifier of the key owner, a timestamp, the whole block encrypted with the CA's private key. And that is referred to as having signed the certificate, basically. Okay. Yeah, so that's kind of the last thing, I think. All right, yep. So that's the lecture for today. So I'll stay for a few minutes until 5:40 if you guys have any questions. So let me stop the video here.